Well, good afternoon and welcome. This is what I want to talk about, and Kingston University still pay me. So my talk has a loose structure. I want to say a few introductory things, and I want to show you some results of experiments, talk a bit about granular temperature as relevant to this regime, show that you can solve a problem, and then talk about a cell model that might be helpful in getting the concepts off the ground. Here is an apparatus as designed by chemical engineers at Loughborough University. Essentially, there is a cylinder here, and the cylinder is filled with a slurry. At the bottom of the cylinder is a so-called septum. That's basically a permeable membrane, and the holes in the septum are smaller than the size of the particles. And we fill this apparatus with a fluid, and we keep that fluid at a constant level, and all this peripheral equipment is there to make sure that the level remains constant in one version of the experiment. And so you get a downflow, and it's a matter of waiting, and all the particles will clog up the holes in the septum, and then the filter doesn't work any further. What we do is we agitate the septum with a vibrator, so it goes up and down. We can choose the amplitude, we can choose the frequency of vibration, and what we're hoping to do then is impart some fluctuational energy to the particles here, which causes them to migrate away from the septum, and then that septum will be permeable again, and that way your filter will last longer. There are certain applications in the world where the changing of a filter is very expensive, especially medical applications. And if any of you here are on regular dialysis, you will know that it takes nurses to come in all the time and change that filter, and with this apparatus you don't have to do that so often, so it makes it cheaper. Also in your car you have filters, which could work better. We've written about this quite extensively, and I want to introduce you to a few collaborators. One of the very important collaborators who also designed the apparatus and was in charge of most of the measurements is Richard Wakeman, now retired from Loughborough, and his research assistant Pyong Woo. They've done most of the experiments. I had a postdoc working on it, Oskan Gondakdu, and then subsequently I had another postdoc, Master Davis, who was a mathematician who enjoyed working on these problems, and recently we had a student take her PhD on it, Samir Vahid, who wrote on slurry flow. The regime I'm discussing here is rather different from what has been presented in the previous talks. My Reynolds numbers are all very small, it's all viscous, and needs a slightly different treatment. I have no turbulent flows, etc. Now, I want to show you a result of the experiment. There you can see the kind of particles we had, a fairly monodisperse medium. We can agitate at various frequencies, and that's indicated by the symbols on the graphs. And here I plot the flow through the filter as a function of the amplitude of agitation. And what you see is, if you agitate small, you don't, it's a slight densification, but you don't see anything, and then suddenly there is a point when the whole thing fluidizes, and then look at this, you go up by nearly a factor of 10 in permeability. So that's no cat piece, that's a real big effect that really clears that septum, and in this regime that septum is as permeable as the clear water value of the permeability or the resistance of that membrane. I'm not going to talk about this critical point. We have theory about it and we've written about it. If I, in these papers we can get that critical point back quite easily by looking at waves through a solid fluid medium where there are enduring contacts, and that critical point depends on the frequency as the square root of the frequency. So I'm not going to talk about that. What I'm going to talk about is this regime here where the stuff is fluidized, and that's intriguing. And the theory I want to use is the granular temperature theory by McTighe and Jenkins, published in 1992. The reason I want to use this, I mean, we're obviously talking about migration problems here. I want to use this theory rather than your Phillips or your Acrevo, any like those, because those other theories all require a mean strain rate field to describe the diffusion, and this theory can also deal with a situation where there's no mean flow, right? So basically in that cylinder, that slurry sits there, it's being agitated, it just sits there quietly, very quietly in fact, if you see the experiment, and so obviously there's a balance between the agitation and the solidosity profile that appears. What we do is the stress is decomposed into an intergranular stress and a fluid stress. The intergranular stress itself is a viscous stress, if there were a mean field, the viscous stress, and a particle pressure. And the viscous stress, let me just take, for modeling purposes, a very simple isotropic model, just with two Lamé coefficients. And the particle pressure is, I suppose in 92 was a new element in the theory, and it's that particle pressure that makes the theory different from an average or from an ordinary fluid, right? So you need something for that particle pressure to make it a slurry. For the, it's all slow flow. For the fluid pressure, we just take the Darcy's law kind of thing, relate the pressure gradient to the superficial fluid velocity with a drag coefficient. So that I'm going very simple on that. And in one dimension, the equation of continuity for the fluid is obviously that, and the stress equilibrium, total stress equilibrium in one dimension is this. There's the particle pressure, there's fluid pressure, there's the gravity term, and nothing else. All in one dimension, very simple. Now, in the granular temperature theory, we look at a rate of working balance. And the rate of working is essentially there, the TZZ times the velocity gradient, which is the mechanical work done, and there is a dissipation term, the gamma bar, and there's also a granular heat flux, and they all have to balance to make zero. I'll talk about that a little bit later. Feel a little bit uneasy about it, and you'll see why I feel uneasy about it. Right? But that is the formulation that is put forward in that theory. These are the two balance equations. You need constitutive equations, Darcy's law already had. For the heat flux, granular heat flux, we use Fourier's law type expression with a granular. I deliberately put the adjective granular and everything because the granular temperature theory. That's the granular heat flux and the granular temperature gradient that gives you the heat flux. The viscous stresses already discussed. And you need a handful of coefficients. You need that kappa bar, you need a lambda bar, you need a mu bar. And the proposal by McTighe and Jenkins is to say, well, it's a very dense slurry, and so the main interaction between the particles will be the lowest order term in the lubrication interaction, and that lubrication interaction depends only on one non-dimensional quantity, which is the surface-to-surface distance between the particles and their diameter, and they call that S. And then, of course, the whole thing scales with the viscosity, which here is eta. And so the viscosity coefficients look like this, with two constants, alpha naught and alpha 1. The heat conduction coefficient, same form, scales with another coefficient, alpha 2, and the dissipation would then be purely on dimensional grounds, be proportional to the granular temperature itself, and also scales with that same factor. Here is the particle pressure. It scales again with the same factor. There's a coefficient alpha 4, and should be proportional to the root of the temperature. And the interesting thing is that approximately the drag coefficient, Darcian drag, can also be written to scale in that same way, although well, that just happens to come out like that. That's just convenient. And the idea is that those parameters alpha naught and alpha 3, the viscosity coefficients and the granular heat conduction coefficients and the dissipation are all of the order unity. So far so good. The particle pressure is a somewhat peculiar beast. The lubrication interaction, obviously, as a leading order term, will go with the relative velocity over the surface-to-surface distance h and proportional to the viscosity. If you had a slurry that oscillated, then the average value of the relative velocity is 0. That is reasonable. If you then calculate the pressure, which is something like, I'm doing it schematically here, the force times the branch vector, and you, for the force, take that lubrication force, you get the sum of all the interactions and the relative velocities divided by h. Now, for every gap width in the slurry, there are as many positive relative velocities as there are negative relative velocities. That is 0. So the average of that expression would be 0, so there'd be no particle pressure, no slurry. Oh dear. Well, that is true if that interaction were entirely correct, but real spheres, as opposed to mathematical spheres, are not smooth. They are rough. And we've argued in the past that if you have two rough spheres and they interact, then you see that lubrication interaction is singular when h goes to 0. In fact, before h goes to 0, the asperities hit one another, and there's solid contact. And that solid contact is then on the way in and the way out, because there's a coefficient of restitution, say it's a collision, makes that the incoming speed and the outgoing speed are different. And the expression there, sum of the interactions, has a finite value, and as a result, you get a particle pressure, and so that alpha 4 has a value. So that is in the background. I can stick to that model. I can do calculations. What I'm going to do here is ignore gravity, which is a reason of other papers where we have elaborated all that. If you do that, there's only one parameter that's important, and it is the ratio of the mean. So here, let me go back. There's a mean flow going down. There is agitation, which causes a particle pressure, which forces the bed to expand. Those two can make equilibrium in some way, and that is expressed by this one non-dimensional coefficient, which is the mean flow downwards and the agitation at the septum T bar, which keeps it afloat. And then the other parameter in is the total amount of solids that you have to put in. And then the rest, the whole theory can be made non-dimensional. Here's the solidosity as a function of non-dimensional distance, non-dimensional in terms of particle diameter. So here we are at the septum, and there we go up. Typical curve you might get is that for the solidosity out of this theory. If you then have more solids in it, or fewer solids in it, then you get this curve. So it all goes down a little bit, as you would expect. But if you agitate a bit harder, then you can see that that septum here, the solidosity at the septum goes down, and you get that kind of curve. You can also try measure solidosities, various degrees of success, and you get similar results. So I don't want to talk about that too much. Now, I want to talk a little bit about the underlying assumptions of the model. And I have drawn here particles, and I'm going to distinguish the particles by Greek superscripts. Then C mu nu relates to the branch vector connecting particle mu with particle nu, and there's a force which I sort of concentrate near the contact, which is then denoted by F mu nu. I've got to hurry up. The lubrication interaction is just the relative velocity divided by h, and then a pile of unit normal vectors to say that it's basically a normal interaction. I know the higher order terms, but leave that aside. And if I calculate the stress on the assembly, and I make the assumption of mean strain, saying that the velocity difference between particles is basically given by the mean strain rate, then I can shove that into that formula, shove that into there. If I furthermore make the assumption that the mean strain is all there is, and nothing else, then all these sums, and that the average distance between particles is all the same, then that is that. The ratio of the particle diameter to the surface distance, there is literature on that, mostly by Torquato. This expression has been put forward, quite a simple expression. There are more complicated expressions. And then all you have to do is evaluate this sum over the unit vectors and the branch vectors. And then you can express it in terms of these Lamé coefficients. You can evaluate those sums in 3 dimensions, and then you find that these coefficients for the Lamé proportionality coefficients for Lamé coefficients depend on the number of interacting contacts, if you're calling that interacting points, in this way. They happen to be the same. You would expect that. And I've plotted that here. Here's the shear viscosity scaled to the fluid viscosity as a function of solidosity. I plot the theory here for the cell for 6 interacting contacts. I probably overestimated a bit here and underestimated a bit there. Let's expect that. It's just a little model. Here is Thomas's best fit, and here's a much used other expression by Krieger. What you see is that this viscosity goes up dramatically when the solidosity goes up. I've done some building work recently. I had to mix plaster, and I can testify to the fact that that is absolutely true. So there's that. Now, the other balance equation is the rate of working balance. And this is where I'm happy to have a load of experts here, because I was trying to relate that to a bit of thermodynamics. If I just look at an ordinary continuum mechanics book, Becker and Berger, one of the best books on continuum mechanics, by the way, the total energy is the sum over the internal energy plus the kinetic energy. Nothing obstructive about that. The first law of thermodynamics would say that if I change the total energy, then I have to either supply heat or work. So the rate of working and the rate of heat extraction and the rate and the heat, just all standard continuum mechanics, relates to the ordinary caloric heat, in this case not granular heat, caloric heat that goes through the boundaries of the element. That's all well known. So, if I put all those together, then this is the well-known formula you get. Now I'm going to do the experiment in such a way that these two terms together are always zero. So I'm going to supply caloric heat or extract caloric heat in such a way that the internal energy is exactly balanced by it. So this is then zero. So the whole rate of working is then just the rate of change of the kinetic energy. And that's the expression I'm going to evaluate in a cell model. Now there's a problem in that the cell, in a particulate sense, and the continuum sense is different. In a particulate sense, there's no sort of smooth boundary. And so what I need, and the velocities of the particles are all defined at their centers, and the force is defined at the contact. So they're not the same. So what I'm going to do is I'm going to I'm going to expand that force with a gradient and evaluate them at the same point where I evaluate the velocities. And now I make the inner product with the particle velocity and I get that expression. There's one more thing I've got to do. I've got to here. The force would come from the lubrication interaction. The lubrication interaction itself is proportional to relative velocity. And so I get a velocity times a velocity. Now careful, because if there are fluctuations in velocity, then fluctuations together also give a contribution, right? Which you don't have for the ordinary. So, long live Microsoft. Eh? So I'm going to expand that velocity in an average term, a gradient term, and a fluctuation. Right? I'll do that for all particles. And then I make one more assumption. And the assumption is this, that the velocity fluctuations will obviously appear as autocorrelates and cross-correlates, right? So fluctuations, products of one particle and another particle, that's the cross-correlate, and velocity fluctuations of particles with themselves, and I'm going to ignore the cross-correlates. And furthermore, important assumption is that the autocorrelate is a field parameter which I can expand in the Taylor series, etc. So these are all assumptions I'm making. And if I then do some straightforward algebra and I work out this balance here, then a bit of tedious algebra gets you to this, where I've now expressed it as a rate of working per unit volume. Expression. I can relate that expression. I don't know why this came out like that. But there's nothing you can do, because it looks good on my computer, in fact. But all these terms I can relate back to, I've got the equation somewhere else, see? To this equation, here at the top. Right? All those terms can be related to that. And I'm making the same assumption that there is a mean field. Right? That's the same, this is the same equation. And then I can identify the gamma bar, the Qi, and the two coefficients. These are alpha 2 and alpha 3, and this is the way they come out. And so, by making a cell model in this way and doing the balance in this way, This is alpha 2, that's alpha 3, and these are equal signs. I'm very sorry, but this happens all the time. The Microsoft I have at home is different from the Microsoft you have here, understand? So, using a cell model, I can estimate those coefficients of the model, and I can put those in calculations, etc. And so my conclusions are, first of all, that dead end filter setup can be described with the granular temperature theory. Secondly, the theory has what I would call a large number of coefficients, or there are some that say, oh, only 5, don't worry, but I think that's a large number. But I think by doing a cell model, I can at least estimate the order of magnitude of the coefficient, but I have to say what I assume. I assume mean strain, I assume there's an autocorrelate and cross-correlate, and that one can be negligible to the other. So that's what I wanted to say. Thank you so much for your attention. I think Jim has a question, and he's entitled to one.
Were you able to say something about the particle pressure?
Not from this cell model, no.
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 But every other coefficient you were able to address.
that coefficient is misty. You could say it's a phenomenological coefficient if you just want to do an engineering calculation, but I find it a bit unsatisfactory. And
sorry to be totally ignorant, but is the relation the particle pressure proportional to the square root of the granular temperature? Is it obvious and well known? The relation.
So, let me see. When there is no mean velocity, yes. Right? Because then the only thing that has a dimension of a velocity is the temperature. Or speed is the temperature. When there is a mean field as well, I'm not entirely certain. It may be approximate, but I think when there's a mean shear field, it may need a certain amount of modification.
The equation for the fluctuating energy of the particles.
Say that again, go on.
The equation for the fluctuating energy of the particles.
Fluctuating energy of the pi, yes.
Can you not have a term, a source due to the fluid fluctuation?
Can you have it, or what do you mean? Can we have it?
Is it clear that it is small?
Oh, I see what you mean. If there are fluctuation in fluid velocity, would they not contribute to that balance? I'm sure they would, yes. Yes. So I've assumed they were small, yes.
But they could be large because there is Stokes number, and you know that Stokes interactions are diverging.
I've not evaluated Stokes number, so I can't say. And anyway, that Stokes number.
No, this is Stokes flow interaction.
Oh, right.
The long range fluid velocity interaction.
No, the assumption of the model is that the main interaction between particles takes place via the lubrication interaction. And the velocity fluctuations are... But wait a minute. I think Luigi and Jim... Oh, sorry to interrupt the conversation. But Luigi and Jim, you're going to have a poster on this, right? In some way. You're going to estimate those coefficients in another way?
That's still a work in progress.
But you're hoping by tomorrow to have this.
I'm more comfortable talking about it privately.
Oh, anyway.
But that's the issue, is the
Yeah.
evaluation of the particle pressure.
Yeah, that's right. Olivier.
Exactly what kind of boundary condition do you use at the vibrating?
Oh, at the vibrating septum, the boundary condition I usually say is the temperature of the particles there is equal to the velocity fluctuations energy, quadratic times a half of the septum. Yeah. Okay. I'll be happy to talk privately.
Let's take it, and the rest is